Welcome from Nexus. In this chapter, we're really going to dig into the nuts and bolts, the components that make up a big data environment. So yeah, let's just jump right in.
So this is the big question, right? I mean, how do you even begin to build a system for this? We're not just talking about storing a lot of data. No, it's about handling this insane, messy, high-speed flood of information. It's a huge engineering problem, and that's exactly what we're going to unpack today.
Okay, so to make sense of all this, we're going to build this system together, from the ground up. First, we'll look at the big data blueprint. Then we'll move on to the foundation, the infrastructure and interfaces. After that, we'll get into the engine, which is all about data organization. And finally, we'll talk about the payoff, the analytics and applications that make this whole thing so powerful.
All right, first things first, we need a plan, a blueprint. And when we talk about a big data blueprint, we're not talking about one single piece of tech. It's really an entire architectural stack.
You can kind of think of it like building a skyscraper, right? You've got all these interconnected layers, one on top of the other. At the very bottom, you have the physical hardware, the bedrock. And way up at the top, you've got the penthouse, the user-facing applications. Every single layer has its own job, and they all have to work together perfectly.
So let's start building. We're going to start at the bottom with the foundation. This is the infrastructure and the interfaces. And let me tell you, if you get this part wrong, the whole thing comes crashing down. It's absolutely non-negotiable.
When you're designing this foundation, you're playing a constant balancing act between these 5 pillars. You have to ask yourself, how fast does it need to be? That's performance. Can it ever go down? That's availability. How big does it need to get? Scalability. How quickly can we change it? Flexibility. And, of course, the big one. How much can we afford? That's cost. See, there's no perfect answer. Every single big data system is a series of trade-offs between these 5 critical things.
This right here is layer 0, the absolute bedrock. And here's the thing with big data infrastructure. You have to design it with the assumption that hardware is going to fail. It's not a matter of if, but when. That's why resiliency and redundancy are so critical. You need backup systems ready to kick in at a moment's notice, so one server dying doesn't take your entire system down with it.
Okay, so once we have our hardware, we need to protect it. Think of the security infrastructure as this protective shell that wraps around the entire stack. This can't be an afterthought you tack on at the end. It has to be baked in from the very beginning, safeguarding everything from the physical servers all the way up to the applications.
So, a question for you. How do all these different layers, and all those external data sources we need to pull from, how do they all talk to each other? Well, that's where APIs come in, the Application Programming Interface. The best way to think about an API is like a universal translator. It's a set of rules that lets totally different pieces of software communicate and share information in a standardized way. And when we're talking about web-based APIs, the big standard is something called REST. The really important idea here is this concept of loose coupling. What that means is REST doesn't create these rigid, permanent connections between systems. Instead, it creates temporary ones. And that's perfect for the internet, right? It's what gives us the flexibility to pull in data from all these dynamic sources, like a live Twitter feed or a Facebook stream.
All right, so our foundation is solid. Now it's time to move up the stack and get into the engine room. This is where all the action happens. It's where the raw data gets organized and where all the real heavy lifting, the actual processing, takes place.
Now, if you've ever worked with traditional databases, you've definitely heard of ACID. It's like the golden rule for making sure transactions are reliable. It stands for atomicity, consistency, isolation, and durability. Basically, atomicity means a transaction is all or nothing. Consistency means you can't write junk data. Isolation keeps simultaneous transactions from messing each other up. And durability? Well, that just means once the data's saved, it's saved for good.
And this is exactly why big data forced us to invent a whole new way of thinking about databases. See, traditional databases, we call them RDBMS, they are all about those strict ACID properties. They prioritize consistency above all else, but that rigidity just doesn't work for big data. So NoSQL databases came along, and they basically said, you know what, we're going to relax some of those strict rules. And in return, we get insane scalability and the flexibility to handle all kinds of messy, unstructured data.
But it's not just about the database, of course. There's this whole ecosystem of services that have to work together. You need a distributed file system to spread the data out across hundreds or thousands of machines. You need serialization services to store that data efficiently. You need coordination services to act as the traffic cop for all the distributed apps. And then you have tools for ETL, extract, transform, load, to get the data in, and workflow management to make sure everything happens in the right order. It's a whole team effort.
So that brings us to the big question.
how do you actually process a petabyte of data? I mean, seriously. The answer, or at least the original breakthrough answer, was MapReduce. This was a framework that came out of Google, and it was a total game changer. It's what made it possible to process absolutely massive amounts of data in parallel, using clusters of cheap commodity hardware. It's really the powerhouse of the whole big data engine. And the way it works is actually beautiful in its simplicity. It's a classic divide and conquer approach. You've got 3 steps. First is map. A master computer takes a huge problem and chops it up into tiny little subproblems. Then it maps them out to a bunch of worker computers. Next is shuffle. Each worker solves its little piece of the puzzle and sends the answer back. And finally, reduce. The master computer takes all those little answers, shuffles them together, and reduces them into one final output. It's this parallel processing that gives it unbelievable speed and scale.
Okay, we've laid the foundation. We've built the engine. Now, we get to the payoff. We're climbing to the top of our skyscraper, the top of the stack. This is where all that hard work pays off, where the raw, processed data gets turned into actual, tangible insights and real business value.
This layer, the analytical data warehouse, this is the playground for the data scientists and the business analysts. It gives them the tools they need to dive into all that organized data. They can run queries, build reports and dashboards, and use really cool data mining techniques to find those hidden patterns, the insights that you just can't see when you're looking at the raw data.
And that brings us to the very, very top of the stack, the big data applications. You know, if all the layers we just talked about are the car's engine, the transmission, the chassis, then this layer is the steering wheel, the gas pedal, the GPS screen. It's the part that the end user actually touches and interacts with to get something done.
And these applications can be incredibly diverse. You've got horizontal apps, which solve problems that exist across a ton of different industries. Think tools like Splunk for analyzing log data. Then you have vertical apps, which are laser-focused on solving a problem in one specific industry, like applications for healthcare or manufacturing. This is really where the rubber meets the road, where all this tech starts solving real-world problems.
So, when you step back and look at the whole thing, here's what it comes down to. We've spent all this time talking about the how. The architecture, the tools, the stack, that's all how you do it. But the technology, for all its complexity, is just a tool. The real question, the much more interesting question, is what? What problems are you going to solve with it? What questions will you answer? That's what really matters.
All right, so what's next? In our next chapter, we're going to dive into virtualization. It's a super important piece of the puzzle that makes these massive distributed systems so efficient. We'll look at how it lets us share physical hardware resources across a whole cluster, adding a whole new layer of flexibility and power to everything we've just talked about. See you then.